to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. My name is G. Sampath. I am going to explain the subject VLSI design. Yes, today we are going to discuss the time delay of NMOS and CMOS inverter. Right, time delays. Time delay, time delay of inverters. So you can say time delays. So what is the time delay of inverters? So time delay is nothing but time delay time delay is time delay is how much time taken of the inverter output, how much how much time taken how much time taken output of the output of inverter output of inverter when input is applied, when input is applied when input is applied. So how much time taken the response of output inverter with respect to input is applied. So it is nothing but a time delay, right? How it will be quick response of the output signal. If output is quick response, the delay reducing. Output is output is quick response. Quick response delay time delay reduced. Time delay reduced. Time delay reduced. Time delay reduced. If output is taking time, if output inverter, let us take it is inverter. Output is inverter. Output inverter. If output inverter taking time to get the output, output inverter taking time to get output, then delay increased. Time delay increased. Time delay increased. Right, every circuit having the time response, how much delay is happening when input signal is applied to the inverter is here, right? So let us see we have different types of inverters. Let us find out the time delays of NMOS inverter and then CMOS inverter. Inverter time delay, NMOS inverter time delay. NMOS inverter time delay. NMOS of inverter time delay. Right? Let us consider how much time delay of an NMOS inverter. Let us consider the two cascading connections of inverters, NMOS inverters. Two cascading connections of NMOS inverters here. Let us find out how much time taken where one signal is applied from here to here, and output of this one goes to this one, and what is the total time taken from input to output, and what is the inverter 1 output, what is inverter 2 output, what is the total output, right? Here inverter 1, inverter 2, it is NMOS inverter, inverter 1 and inverter 2. The input is applied here, logic 1, right? We are applying logic 1, 0 to 1, 0 to 1. V in we are applying, V in we are applying, right? Here is a output, here is the output of this second inverter, and this one is the output of V inverter output, first inverter output. As a input to this one, then we'll get the output, right? What happens here? What happens here? When V in is equal to 1, we are applying. Let us it is NMOS inverter, and we know this NMOS inverter, and we know the NMOS inverter, right? One is a depletion mode transistor, pull up is depletion mode. It is a circuit representation. I'm drawing this in circuit representation, right? This is a circuit representation, NMOS inverter, and above is pull up transistor. We call it is pull up transistor. This is pull up transistor. This is pull down transistor. V input is applied, and we are getting output over here. If you are applying logic 1 here, okay, logic 1 is here, we are applying. 1 is here, what happens? This one, what happens? Inverter, what happens? This in inverter, depletion mode transistor is always on, it is always on. Enhancement mode, this will be on, right? This will be on. 1, it will be on, right? If you are applying 0, if you are applying 0, 1 to 0, then it will be open circuit. Then it will be open circuit, off. Okay, let us see this one. If your 1 is applying in NMOS inverter, enhancement mode is on. Enhancement mode is on. This will be on, right? So output is 0. Output is 0. 0 goes to this inverter 2. 0 goes to inverter 2. What happens? This will be off. Enhancement off. Enhancement is off, right? Output is 1, right? Output is 1. So this is a cascading connection. Input 1 is applied, output is 0, inverter output is 0. As a input is second inverter, our output is 1. Now we have the time delay Td is equal to 1 plus jet pull up by jet pull down into delay unit. Tau is a delay unit, right? So here it is the pull up pull down ratio is, inverter is having the pull up pull down ratio 4 by 1, here also 4 by 1, right? This is 4 by 1 and 1 by 1, 4 by 1, 1 by 1 ratio. So we can say it is 4 by 1 and 1 by 1. Pull up is 4 by 1, pull down is 1 by 1. So it is jet pull up, jet pull down ratio, where jet pull up, jet pull down, here jet pull up by jet pull down, jet pull up by jet pull down. So it is a jet means impedance. Jet means impedance, where Z is equal to length by width ratio, where Z is equal to length by width ratio. So the resistance is nothing but length of the channel, width of the polysilicon, width of the polysilicon. So that is a jet pull up and jet pull down, length and width parameter. So the jet is depend on the, here you can see this is the length of the channel, width of the polysilicon, length of the channel, width of the polysilicon. Right? The pull up pull down ratio should be maintained because there is a static current to flow through this one, static current to flow through this one. So whenever it will be connected in cascading, right, the output should drive the second inverter. In order to drive the second inverter, it should be maintained some length and width ratio. So there is a pull up pull down ratio. So there is a power dissipation problems occur in NMOS inverter, but not in CMOS inverter because pull up pull down PMOS is a complement of NMOS in CMOS. CMOS PMOS is a complement, and NMOS and PMOS are equal in size, but not NMOS inverter not in equal in size. It is a 4 by 1, it is a 1 by 1 ratio, right? In order to drive the second inverter, it should be maintain the pull up pull down ratio, right? The formula is for time delay. It is a time delay of the inverter. It is NMOS inverter. The formula is TD is equal to 1 plus jet pull up by jet pull down, where jet pull up by jet pull down is, what is the ratio is given here, 4 by 1 is given, 4 by 1 is given. Okay, then you can substitute this one in TD formula. Then TD is equal to 1 plus jet pull up by jet pull up by jet pull down into tau, right? This will be equal to 1 plus jet pull up by jet pull down, how much? 4 by 1 ratio is given. So it should be maintained the 4 by 1, 8 by 1, 16 by 1, like that. It should be maintained length and width ratios. When it will be in cascading connection, there is a static power and depletion mode transistor. So it will be connected to another transistor, or the inverter is connecting through the pass transistors. It will be maintained some this jet pull up jet pull down ratio, right? So it will be 1 plus 5, 1 plus 4, 1 plus 4 into tau. This will be equal to 5 tau. The total time delay is 5 tau. It is a total time delay. TD total time delay is equal to, the total time delay is 5 tau. Let us see this one more. Right? How much time delay total from here to here is 5 tau. Let this one from here. Right? From here to here, right? From here to here, the total, what is the total time delay from input to output? Total is 5 tau, right? Tau is in nanoseconds. 5 tau. Total is 5 tau. You see this one. According to this 4 by 1 ratio, the total time delay when input is applied, it is a cascading connection of the inverter 1 and inverter 2. It is NMOS inverter. So what is the total time delay? It is 5 tau. 5 tau from input to output. Now what is a first inverter time and what is the second inverter time? What is the on time? What is the on time of this inverter? What is the off time of this inverter? It is simply saying that 1 plus 4 tau. So 1 is the on time and 4 tau is the off time, right? So here I can write this, where 1 tau is on time inverter, on time inverter. 4 tau is a off time inverter, off time inverter, right? So here you should mention 1 tau is the, so from here to here, From here to here, how much it is? From here to here, how much it will be taken? 1 tau, right? So it is 1 tau. So when it will be on, the time taken here, 1 tau. So from here to here, the output from here to here is, so from here to here we can take the time. Off time is, off time is 4 tau. Off time is 4 tau, 4 nanoseconds, right? Yeah, this one. On time is 1 tau. Off time is 4 tau, because where the 4 by 1 ratio, 4 by 1 ratio. So 1 is the on time, 4 is the off time. 1 is the on time, 4 is the off time. So when the inverters are in cascading connection, total time delay from input to output is 5 tau, 5 nanosecond input is applied, then output is taken 5 nanoseconds. The first inverter time delay is 1 tau, and the output of first inverter as a input to this one, then this transistor enhancement is off, then we will get the output. So off time will be taken the 4 tau, right? 4 nanoseconds. So that is a inverter to inverter, NMOS inverter total time delay. If you are taken if you are taken Z pull up by Z pull down is equal to 8 by 1 ma. You tell me this, what is the on time, what is the off time, right? So 1 tau is 1 tau is on time, 1 tau is on time, and 8 tau is the 8 tau is off time. So total time delay from inverter to inverter, if it will be maintained 8 by 1 ratio, so 1 plus 8, it is 9 tau, 9 nanoseconds of time. So this is the time taken. Let us take it will be 8 by 1, 16 by 1. So 16 by 1 means 1 is on time, 16 is off time. So like that it will be taken, right? Now, if you are taken a CMOS inverter, if you are taken CMOS inverter, if you are taken CMOS inverter, inverter with equal transistors, PMOS and NMOS. So CMOS inverter is designed by both PMOS and NMOS. If both are equal in inverter, right? Equal in inverter, right? It will be taken like the inverter is here. It will be designed by CMOS. So what is this inverter 1 to inverter 2 output? Like it will be taken, the input is same. It will be 1. It will be 1. We are applying inverter 1, inverter 2. So if you are applying 0 to 1, this is V in and this is V out, right? Right? If it's, whenever it will be equal, NMOS and PMOS are equal. NMOS and PMOS are equal. Here in this, there is no power dissipation, there is no static power dissipation. That last class we discussed in NMOS NAND, CMOS NAND, logic gates. In logic gates we discussed it. So when NAND of NMOS time delay is enhancement n times, but here equal, PMOS and NMOS are equal. There is no static current. There is no static current in depletion. Like both are equal. So V in equal to V in input and this is output signal. Both are equal. So no need to maintain this pull up pull down ratio. No need to maintain pull up pull down ratio. If the resistance of this one, if the resistance of this one, it is R pull up, R pull up is 25 kilo ohms, and this R pull down is, the pull down transistor is, if it will be maintained, R pull down is, resistance of this one is 10 kilo ohms, right? According to this, according to this, so R pull up by R pull up pull down ratio, right? R pull up by R pull down is equal to 25 kilo ohms by 10 kilo ohms, right? It will be 2.5. So the inverter 2 pull up resistance is 2.5 times of the first inverter pull down resistance, right? According to the resistance pull up pull down ratio, so how much time taken of the second inverter is 2.5 times, 2.5 times more than the first inverter pull down resistance. So let us take this one, the first inverter time is, let us take from here to here, if it will be, if it will be 2 tau, it will be 2 tau, let us take, it will be 2 tau. Now what about this one from here to here, from here to here, how much it will be? 2 into 2.5. So 2 into 2.5, how much it will be? 5 tau, right? It is a 5 tau. Okay, 5 tau. So 10 kilo ohms, 25 kilo ohms, if we take the ratio 2.5, so 2.5 times more than the pull down transistor 10 kilo ohm resistance. So it will be taken, let us consider, it will be 2 tau. So the second inverter time is 2.5 times more than 2 into 2.5. So it will be 5, right? So the total time delay from here to here is, the total time delay from here to here, total time delay is how much it will be? How much? So 2 plus 5. Total it is 7 tau, 7 nanoseconds. Total 7 tau. Like that we can take in the CMOS inverter time delays if there is no pull up pull down ratios. There is no pull up pull down ratio, because with respect to this resistance we can find out the, time delay from inverter 1 to inverter 2 CMOS. Now there is a formal estimation of, a formal estimation of, so basically we use resistance, but basically a formal estimation of, a formal estimation of CMOS inverter time delay, CMOS inverter time delay. If resistance is not mentioned, CMOS inverter time delay. If resistance is not, if resistance is mentioned, then we can go for this. If resistance is mentioned, pull up, pull down, then the ratio will be taken. The second is how much than this one. Let us take 2 tau. Then it is multiplication of second pull up resistance ratio. Right? There is a total time delay from input to output. If the resistance will not given, a formal estimation of CMOS inverter time delay, right? A formal estimation of CMOS inverter time delay. So it can be taken, it can be taken by the two ways. First one is rise time estimation, rise time estimation, rise time estimation. So basic CMOS inverter, right? It is a inverter to inverter. It is inverter to inverter. The cascading connection of inverter to inverter with the CMOS. If any CMOS inverter, if any one inverter can be taken as, if any one inverter can be taken as rise time estimation. Second one, fall time estimation. Fall time estimation. Let us take in one inverter. It is a rise time means TR. It will be TF. Let us see the first one. First one, rise time estimation. Rise time estimation. Rise time estimation TR. Let us see this one a circuit. The rise time of the output. The rise time of the output. So when it will be taken, this is a PMOS transistor, right? PMOS transistor. Below one is a NMOS transistor. PMOS transistor, NMOS transistor. So this is VDD and this is VSS. CMOS inverter means PMOS transistor and NMOS transistor. The current flow through the PMOS transistor is IDSP, right? Whenever we are applying input is whenever we are applying input is so 1 to 0 V in we are applying so the output of this one is load capacitance. The capacitance, load capacitance, can take the load capacitor. So load capacitor, here we can take output across the capacitor, V out. Here we can take the output, right? When 0 is given, so which one is on, which one will be off? Let us see this one in a circuit model, transistor circuit model, right? If you are applying 0, PMOS on, NMOS off, NMOS off. So NMOS off, disconnected. Then output is equal to VDD. Output is equal to VDD or 5 volts or logic 1. Right? Output is VDD. Like V out is equal to, it will be raised. Then it will be raised from 0 to 1. It will be raised 0 to 1. It will be raised 0 to 1. Right? So where IDSP, drain to source current of PMOS transistor, it will beta P into VGS minus, is the magnitude of VTP plus or minus magnitude of VTP whole square by 2. Then we can take the output voltage. Output voltage is equal to IDSP into T divided by load capacitance CL. So this can be taken as like we have how we got this one. So we have capacitance. Capacitance is equal to charge per unit voltage, right? The charge is equal to capacitance into voltage, right? Differentiation both sides. dq by dt is equal to c into dv by dt, right? So what happens? Dq by change in current, change in charge with respect to time, it is current I, right? So c into dv by dt, right? So if you take the integration both sides, If you take the integration both sides, what happens? So integration both sides, integration derivation will be cancelled out. So V, output voltage V. So from this capacitance, capacitor output voltage. Now I can take the V out is equal to, from V out is equal to 1 by CL, right? 1 by CL, integration from the time limit 0 to T, I dt, right? I is a constant. I is nothing but current flow to the PMOS transistor. So I is nothing but IDSP. I can take IDSP by CL, right? Integration of 1 with respect to T means it will be T, right? Into T time duration T. So this is we got V out is equal to IDSP into T by CL, right? Then V out is equal to, substitute this IDSP. What is IDSP? Beta P, beta P, VGS minus magnitude of threshold voltage of PMOS transistor, whole square by, whole square into the T as it is, you can write, divided by 2 is there. So 2 into CL. Okay, then substitute where T is equal to, where where T is equal to TR, rise time, and V out is equal to, VDD. You can substitute here. Now take this, what is the T in equation T? TR. Write this equation. TR is equal to what happens? 2 into CL V out by, here is multiplication. If you take this left side, it will be dividing. Beta P, into VGS minus VTP whole square. Right? V out is equal to VDD. VGS also you can substitute VGS also VDD. Right? TR is equal to, so 2 into CL, 2 into CL. V out is equal to VDD. So divided by beta P into VGS is nothing but when it will be on, the VDD flows through. VDD flows through. So VDD minus plus or minus, it will be VTP is 0.2 VDD. 0.2 VDD whole square. Right? If you simplify this one, VDD and VDD square will be cancelled out. Right? 0.1 minus 0.2. It will be 0.8 VDD whole square. So square and VDD will be cancelled out 2 by, right, 0.8. Then it will get the value, it will be 3 CL by beta P into VDD. Right? This is a rise time of, capacitance, output capacitance. Rise time of output capacitance when CMOS and PMOS is on. When PMOS is on. Right? PMOS is on. So let us take the second one. What is the second one? Fall time estimation. Second one is a fall time estimation. Same. Fall time estimation. Fall time estimation is nothing but a TF. Right? Fall time estimation. So here we can take the circuit representation, and above one is off, below one is on. Now this is NMOS transistor. Now we can take the capacitor over here. Now output is taken from here to here. V out and load capacitance. The current flow through this is IDSN. The input logic is applied. It will be 0 to 1. See, 0 to 1 we are applying. So V in 0 to 1 means 1 is applied, NMOS is on, PMOS is off, disconnected. Right? Output voltage, what happens? It will be fall down. Right? From 1 to 0. Fall down. It will be 1 to 0. It will be 1 to 0. So the equation will be taken IDSN. IDSN. So drain to source current of NMOS transistor is equal to beta N. So beta N, right? VGS, same thing. Only instead of PMOS, we can place the NMOS. VGS magnitude, we can take VTN whole square by 2. Similarly, Vout equal to previously what we got IDSN into T by CL, load capacitance. Right? I can write here. So what happens? T is equal to TR, T is equal to TF. Sorry, T is equal to TF. Now Vout is equal to VDD. Vout is equal to VDD substitution. What happens from this equation? Now TF is equal to 2CL into Vout divided by beta n VGS minus VGS minus VTN whole square. So substitute VGS VDD, Vout is equal to VDD. Now 2CL Vout is equal to VDD, VGS is also VDD, right? VDD minus zero point 0.2 VDD, threshold voltage, zero point 0.2 VDD, right? Zero point 0.2 VDD, it is 1 volt, right? What happens? This one TF, the final equation is equal to 0.8 VDD. So 0.8 VDD whole square. So it will be 2 by that 0.8. It will be 6.4 like we'll get. Then if you take the ratio, we will get this 3CL divided by beta n, right? Beta n into VDD. This is the final equation of fall time of NMOS transistor is on. NMOS transistor is on, right? This is the equation. Now, here what is the beta n, right? Beta n and beta p. Let me write here. Beta p is equal to, we discussed in CMOS inverter, or we discussed in IDS versus VDS relation. Epsilon naught mu n by d into Wn. Okay, width of the polysilicon n type. Sorry, it will be P is there. Okay, you can write it is WP, right? WP. So we can write it is mu P by D into WP by LP, right? This is beta P. Beta N is equal to same. Instead of this P, we can place N type. Epsilon insulation, epsilon naught mu N by D into Wn by length N type, right? Length N type. So this is the CMOS formal estimation of rise time and fall time. It's a very important derivation. Will be asked, calculate the time delay of the CMOS inverter, rise time and fall time, right? So summary, let us write the summary. Summary of CMOS rise time and fall time. CMOS rise time and fall time. CMOS rise time and fall time. So we have seen the ratio. So T rise time, T fall time is equal to beta P by beta N, right? Where where beta N is equal to Beta n is equal to the mobility of charge carriers are faster than the mobility of charge carriers of p type, right? So mobility of holes are moving slowly and mobility of charge carriers are faster and more per unit area, like 650 volts per centimeter, and it will be mu p is a 240 volts per centimeter that we discussed in ideas versus VDS relation. So beta n is 2.5 times of beta p. So here we can estimate this TR rise time. TR and TF are proportional to proportional to proportional to 1 by VDD, right? Proportional to 1 by VDD. And second one, TR and TF are TR and TF are proportional to proportional to proportional to CL. If you see this one, here also inverse relationship with the 1 by VDD and directly proportional to CL, right? In this also, so inverse relationship with the 1 by VDD and directly proportional to CL, right? Both are TR and TF are proportional to CL and proportional to 1 by VDD, right? Now TR is the time taken of the PMOS inverter is so 2.5 times of the fall time of NMOS inverter. So when P when PMOS and NMOS are equal, when PMOS and NMOS are equal, PMOS and NMOS are equal geometry or equal geometry means equal area. If it will be P and N are both are equal, then the time taken, the rise time of PMOS inverter is on, NMOS inverter is off. So PMOS transistor. PMOS transistor time is 2.5 times of fall time of NMOS transistor. Right? The mobility of charge carriers is more, mobility of charge carriers are less. So time taken to on the transistor. So it will be the time taken with the rise time is 2.5 times of fall time. So this is about NMOS inverter time delays and CMOS inverter time delays. So it will be asked in the examination CMOS inverter time delays. Okay. So please subscribe our channel, like, share with your friends. Okay. Then you get more knowledge by this channel. Okay. Thank you.